Okay, cool. This is always the point in time where I just really gotta check if we're live. Going live, live now. But I think we're looking good. Just making sure that YouTube is indeed picking up the signal. Not yet. It is time though. Yeah, okay. I can see myself. This is great and cool. So today what we are doing is I really like doing. So I I don't remember when, but a while ago I read this blog post from Mate, and I hope I pronounced your last name correctly, Mate Kalishko. Eventually, we found each other on LinkedIn as well. But what I really enjoyed is that people are still writing blogs and that they're also sharing cool ideas. People have sort of forgotten how to do that, it sometimes feels like, but I am a huge fan of stuff like this. I'm not gonna go through all of the code in this blog post, but the main thing I would like to mention is that there's an idea in this blog post, and I re-implemented it, and I also made it scikit-learn compatible. And we'll talk about an implementation that you can download soon. But before doing anything, like I do want to strictly mention this is super cool. Everyone, if I can do anything to your career, start a blog and let's share cool lessons this way. Because this was a really good read. But the most important thing is there's also, I think, a cute idea being presented here that deserves a little bit of extra attention. So, um, I'm gonna give my version of the story but in order to do that, I will also simulate some data. So, what is the blog post kind of about? Well, the blog post is about splines, and splines can kind of be seen as this interesting way to add features to a machine learning pipeline, especially for linear models. It's kind of a useful thing. So we need a data set to start out with. I'm inside of a Marimo notebook, and what I'm just going to go ahead and do is make it full screen. And I've also drawn me a little data set over here. But just for good measure, let's just reset, and I'm just going to make a data set that looks a little bit like this. Okay, so this is a time series data set, basically. I've got an x-axis over here, I've got my y-axis over here, and the whole point is I've got my x value, and I would like to predict the y value. That's the goal of this data set, so to say. Okay, so this is the scatter widget. I've mentioned that earlier in different streams. But what's kind of nice is that I can then start thinking about features that I can generate in order to get a linear regression working for this. And feel free to take a moment, like, okay, what can we do to sort of still get this shape fitted? One thing you could do is you could say, well, let's take this entire span, if you would, and let's just, put it into separate bins. So we're going to bin the thing up, bin, 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 right? And then we're basically going to have one hot encoded variable. So this is feature 1, this is feature 2, all the way up until whatever feature k, right? And then some sort of algorithm can figure out some sort of a mean for all of these one-hot encoded variables, so to say. And you can, it is going to be like a very jumpy kind of a model you're going to be able to get out, but you are able to do something like this, right? Like you are able to generate these one-hot encoded features just like that. From a modeling perspective, though, like one issue I would have with this is the fact that it is kind of spiky. Maybe you want to have a prediction that's a little bit more smooth, because in the end, that's also what the data shape is like. But I think to me, most of all, the thing that kind of bothers me is it does kind of feel that if I want to make a prediction for the point that's like right over there, then at the moment, the only points that can influence that prediction is stuff on basically the right-hand side. Even though there are points over here that are closer, these points are going to have more of an influence on predicting over here if we are really going to go through this binning approach. And that just doesn't sit well with me. If in the end, like the heuristic here is that proximity is going to be the thing that allows us to make a prediction, then we should take it serious. And one hot encoding it in this case is not going to get us there. What we can do is kind of like a similar trick. What I still can do is I can say, well, I'm going to be cutting this space up a bit, but instead of really cutting it with like hard cuts, what I can also just do is say, well, let's pretend that there's like a little knot here, so to say, and I'm just going to generate me a hill kind of around it. And I'm going to generate me another knot over here, and I'm going to generate me another hill kind of around that. And I'm basically just going to fill this entire span with hills, but the point is that these hills will overlap. Now, in this case, right, there's a lot of hyperparameters, I guess you could say. You can do things like, hey, what's the width, and can we be principled about it? But hopefully by doing this and having features that are not necessarily super one-hot variables, but more things that are overlapping, well, if I now want to make a prediction of a point that's like, let's say smack dab in the middle over here, right? Then you are going to see that a lot of influence is going to come from these two hills instead of just one of them. And that's kind of the situation I would love to be in. And this is something you can actually do with the scikit-learn spline transformer. And I'm just going to give you the quickest demo of that. And that's fairly easy to do inside of a Remo. So let me just zoom out. Actually, I can hide the code, I think. Yeah. What's the shortcut for that? Command H. Okay, so the code is hidden, but the UI elements are definitely still there. Right, okay, so that's pretty cool. So for the data set that I've just drawn, what I can do inside of, I need to show the code actually. What I can do is I can come up with some sort of a scikit-learn transformer, that's a spline transformer. I can tell the spline transformer like, hey, just have 2 knots, or like have a bunch more, have many. And we can then say, hey, let's make these hills basically to span up the entire space. That's basically the stuff that's happening here. And let me just find, that is one downside of Marimo, is you do have to find where the code is, because you can move cells around, but there we go. What you're looking at here is really just a spline transformer. The number of knots is a hyperparameter. The kind of knot is a hyperparameter, and the degree is a hyperparameter. And these are things that I can change basically from here. So let's just, yep, and then hide the code like so. But you can see there's an x-axis over here. It starts around 0, it ends around 800. That's about the size of this drawing over here. It starts at 0 and there's like 800 pixels. That's where the x-axis comes from. And you can see that the spline transformer really just allows me to, you know, basically have less or maybe more hills. That's basically the big idea here. There's extra features I can do, by the way. They're kind of cute. I can say I want to have a sort of a 1 degree polynomial, and then stuff just gets super duper linear. That's the thing that I can do. But another thing that I thought was kind of cute too is you can also have the setting where instead of having all of these hills be equidistant, like we're going to take the entire space and cut them up into equal bits, we can also say, well, let's have the placement of the knots be determined by the location where there's more data. So one thing I could do now, just for illustrative purposes, I can add way more data to the center over here. It's just like way more data. And then if I go back down, you should see that the the spline transformer just adds lots of smaller splines there because there's more density there, and therefore there's also more sort of area to cover. So, so far so good, right? Like this is kind of useful. This is kind of neat. And what you can then from here on do is you can also say, well, let's put some of these features into a machine learning model. And when you do that, I'm just going to give it to a ridge regression here. Then you can see that it is actually quite good at fitting some sort of a non-linear curve, so to say. It's not perfect, right? That's totally not the point. But it is cool to see that with this feature engineering trick, you are able to get something that's like super non-linear working in a linear model. And it has a couple of like cool benefits. You can do like statistical testing in order to remove features. There's stuff that you could do. But okay, this is the spline trick. There's lots of old school books about statistics that use this. And to kind of put it up into matrix form, the way that this would basically work is you have your you have some sort of input array X. That's something I've got here on the X-axis. And using the spline transformer, you're basically just generating features from X. So I've got like feature 1 out of X all the way up until like some sort of feature K out of X. And you basically get this giant matrix that represent all of these hills, basically. And the number of knots that you're generating that influences how many columns you're going to get over here. But it is really just a feature generating trick. So far, so good. Note that if you're doing stuff in time series land, you can also apply a trick where it's a little bit outside of the scope of today, but there is this thing where you can say something like, hey, This is a hill that kind of goes up every February, so to say. So like a repeating pattern. That's something that the scikit-learn transformer can also totally do. There's different live streams and episodes I've done about that. But the next question, and that's also the point that the blog post makes, like all of this is pretty useful and like kind of cool, but you can also wonder, well, can we maybe do something with this just to sort of really cause different modeling behavior? Because it's one thing to have a really cool feature engineering trick, but if you do something interesting to this, it turns out that you can also cause a modeling trick. And the easiest way to explain that is to just show you a chart, which I made below. So I'm just gonna move this down. Before going on the next explainer, it will be, if there are any questions, this would be an excellent point in time to ask, by the way. And oh, cool. I study things. Hi from Korea. Hello there. But okay, like assuming there's no like extra questions, like one thing that I can say now is like, okay, we've got all these features, but what if, right? I have this blue line over here, and again, if I remember that array, that's X, and then we have this big feature matrix over here, right? With like f1 of X, and then all the way up until fk of X. I could say, well, let's grab that first column. Let's assume that that's this blue line over here. So that's this one. And let's maybe, you know, take the cumulative sum. So instead of having something that sort of stays flat here and then goes up and then kind of goes down again, like one thing I might also try and consider is just something that can like, you know, it's we're just going to take this value, add that value, basically so we have something that can only go up. Because you'll notice that all the features that I'm generating over here, they are strictly positive. Like they might have the value 0, but none of them have a negative value ever. So that means if I take a cum sum, that also means that I get interesting shapes, so to say, but they will never ever be below 0. And this is what that looks like. Like if I take the blue line, it kind of starts high, and if I take the cumulative sum, it's kind of like taking the integral of a normal distribution kind of a shape, feeling kind of. So you can kind of see the S-curve in some of these. But basically you can see, hey, you know, I'm adding, and at some point it caps off on top or something like that. But what if we put, well, what if, right? If we, like, can we still get interesting shapes fitted if we use these features? Is kind of the brain fart experiment here. Like, I can use these features for sure, but these features might also be good for a machine learning model. And that's something that I'm showing below over here. So the prediction line that you see over here is with the normal splines. These are the normal hills. But I also made a prediction line below over here that effectively does the same thing, except that it takes those cum-sum features. And as you can see, if I do that, I mean, the patterns is, of course, slightly different, but the linear model is able to manage. Like, we are still able to fit a curve kind of nicely. And, okay, so that is curious, and we can think about why that might be, right? Because this is maybe not necessarily the most obvious thing. But you can imagine, of course, that all of these lines can be reweighted, and whenever there's like a sort of a hill going up, you can imagine, oh, that's kind of like a change point. And of course, the linear model in this case can also determine that, hey, the pattern needs to be negative. So if maybe a line needs to go down, they can just add like a negative weight to one of these lines. There's also something a logistic, like a linear model can just go ahead and do. And that is why we're still able to get a pretty okay fit out of this. It's somewhat counterintuitive initially, perhaps, but we're really able to reweigh all those lines until we get like a good mean squared error over here. So that's actually kind of interesting. Like we're able to also do functions upon functions in order to get this thing to work. But hang on. I'm still dealing with features over here that are strictly positive. And what I could also do, at least in scikit-learn land, like, is I can tell ridge regression, linear regression, and I believe a couple of other models as well, that we only allow for strictly positive weights. And that means that if I generate features that look like this, that are monotonically increasing and then capping, you know, if I say, well, let's set the strictly positive flag to true, then suddenly I have a very general featurizer that can cause the model that follows after to be strictly monotonic increasing. And that is kind of interesting because um, it is sort of an underappreciated feature of a lot of these machine learning models, but sometimes you are dealing with a situation where you just know for sure that the pattern that needs to go out is monotonic decreasing or increasing. An example here is that smoking is bad for your health, but it is the case that younger people tend to smoke more than older people. A lot of once people start having kids, they sort of stop smoking. But if you're not careful, then you get a Simpsons paradox that says, oh, the more you smoke, the healthier you are, because the more you smoke, the more likely it is that you're younger. However, the relationship between smoking and health should always be strictly negative. Like if I'm smoking more, I should be less healthy. And having some sort of a monotonic constraint where you're able to sort of declare, oh, but that feature, even if you do these nonlinear featurizers, I 100% need that effect to be negative. That is now something you can actually enforce. Like you can come up with featurizers that allow a ridge regression, so to say, to really only have a strictly positive output, so to say. And that's the whole trick. Like I thought it was just kind of a cute brain fart, so to say. And I initially, you know, I don't know how applicable this is. I don't know if like there's that many use cases of it, but I do really appreciate the, oh, it's a brain fart. Let's just go ahead and explore it. Oh, it does kind of work. Okay, that's actually kind of useful maybe down the line. I don't know if you're gonna hit use cases for this like every single day. It might not be that common, but I do want to encourage people to just get creative with their modeling techniques as well as their featurization techniques, so to say. And again, like I really like reading these kinds of blog posts. So yeah, that seems to me like a somewhat general way to get monotonic features going. Like I thought that was just super duper cool and super duper interesting. One thing I do wonder now, though, now that I'm sort of thinking out loud. Okay, let's test one thing. So I'm kind of wondering now, like, okay, these features are of course um, strictly positive and all that, but I'm kind of wondering, what if I take a ridge regression here with with these normal features, and what happens if I just say, hey, positive equals true here? Yeah, let's do that. See what happens. Yeah. Okay. So yeah, that's actually the interesting thing. So you can. So the thing is, if I set the positive flag to true for these features, then the general pattern is that indeed I am going up, but you see two mistakes with it. One of them is that at the beginning over here, I'm just sort of overfitting, and I'm kind of underfitting over here, so that you have that aspect of it. But you also see that it doesn't necessarily guarantee monotonicity, because over here you can actually see that we're going back down again. And that's of course kind of logical if you consider that we could have a feature over here that kind of just, this feature over here isn't strictly monotonic, so this is going down over here. So you do need to add that feature trick, so to say, to really guarantee monotonicity. Just adding a positive flag to a ridge regression is not enough if the features going in are not strictly monotonic. But again, doing this feature trick totally does allow for it. So this would be an excellent point in time to ask questions. What I kind of want to show you is kind of like a high overview picture. So I'm going to toggle the app view, and I might need to sort of zoom out a bit here. So one thing that's kind of cool about this view, but let's just add this UI element over here. Let's remove this one. And let's add this one. So I'm going to turn the code that I just wrote into kind of an app, so to say. I need to move that. I need to move this one down a smidge. No, I need to. Yes, that one has to move down a smidge. And then hopefully I can scroll down here and get this guy to sort of be about this shape. Yes, that feels good. And then what I should be able to do from here. Yep. Okay. So what I can do from here is I can go back to V. I can tell my Remo now to stop. And I can then tell Marimo to not edit this notebook, but to actually run it as an app instead. Having an response. Yeah, okay. So this thing is now closing. That's good. And then I should be able to source then bin activate, and I should be able to say Marimo run splines.py. There we go. And the cool thing kind of now is I just have a sort of a bigger canvas, and I should be able to, yeah, there you go. I can kind of zoom in. But the cool thing now, just for like a final demo of like just the idea, is I can make my drawing, right? You can see on the left-hand side over here, just the features that are generated with the spline transformer. Then over here, you see the come sum features. And, you know, I can say like, hey, let's go for quantiles, and let's go for like a one-dimensional featurizer. Let's add more knots, and you can kind of see, you know, what the model kind of looks like over here. And I can say, hey, make it strictly positive. And you can see that that has an effect. And I can also compare it to like the isotonic regression inside of scikit-learn. Isotonic regression in scikit-learn, I'm going to open the docs in a bit, is a really interesting algorithm. It's just that you get very spiky results. So it jumps up and then it sort of goes back down again real quick. And kind of the benefit of doing it this way is you at least you still get slightly spiky behavior at times, but you do get something that's just a little bit, shall I say, smoother. So that's also like something that's interesting. So what I'm gonna do now is quickly go to the scikit-learn docs on that one. Let's go out of full screen mode. Isotonic regression sklearn, because that's something I kind of want to show as well. There you go, the docs pages, and if I go to the user guide, there we go. You kind of see an interesting definition of isotonic regression. So isotonic regression is a linear model inside of scikit-learn that really guarantees monotonicity, but it's basically like we're minimizing the error. That's totally something we're doing. But for every prediction that we make, the prediction on the left is always going to be smaller than the prediction on the right. Like if I have a X value that moves, like this is something that I'm totally going to do. But numerically, I was sort of thinking about this, and I was kind of wondering, you know, okay, this is a solvable convex system, I think. Quadratic criterion function, all right, linear constraints, like, okay, we can kind of get there, sure. But do remember, if you have 1,000 points, let's say, then you're going to have 1,000 constraints. If you have 10,000 points, then you are going to have like a solver that has 10,000 constraints. So part of me was wondering, like, hey, this isotonic regression, and to be honest, this was the reason I was actually interested in this blog post. I was looking at the blog post and I was just kind of wondering, like, hey, if I want to have a monotonic regressor, maybe doing it in the feature space and then having like a strict linear solver, maybe that's quicker than having to deal with all of these constraints. So it's not just the fact that I get a regression line that's a bit more smooth. It is also the fact that less constraints typically means a faster algorithm. And turns out that that's actually kind of the case. So what I'm going to do now is rerun the notebook again. That shell is frozen. So Marimo edit spline. There we go. Up. So this thing is going to start up. I'm going to just draw me a little data set over here again. That all looks good. But if I recall correctly, at the end over here, I have a little benchmark over here, which I do want to kind of share. It's not a, like, don't bet the house on the benchmark, but I do think it's kind of cool and interesting. I'm just going to uncomment this stuff and have it run. And then I'm going to uncomment this stuff and have it run. What I have found is if I just look, not at the feature engineering, but if I just look at the time it takes to train a ridge model, and if I were to compare that to training an isotonic model, then I have found that at times training the ridge model is actually more expensive than training the isotonic model. But then if I start drawing just a whole buttload of extra points over here. Like I really will make sure that the pattern that it has to fit, that has a lot of data in it. So I'm gonna make this kind of a chunky line, so to say. So lots of data points. Gotcha. And then I see that, okay, there's more data now. They're about equal now. It seems that they're roughly on par in terms of training time. And I think I've added like an inflation factor over here. If I make the data set like 10 times as big, this benchmark will take a bit longer to run, of course. But at some point, I recall running this the other day and also just seeing there being a difference. So yeah, this is definitely a bit, this ran a bit quicker. I do want to see the number over here. Yeah, so like, I'm definitely cherry picking here, right? So again, don't bet the house on this. This is benchmarking with a cherry pick involved. So like, don't bet the house on this. But I do see evidence, at least, right? That's the key word here, evidence, that if you are going to do something like this, it is actually maybe quicker to do this with Ridge and then the monotonic feature trick. That is just an observation that I've got over here. So, you know, I still don't know how pragmatic this is. I don't know if you're going to need this for everything. The kind of annoying thing with this is that you probably, if you're going to use a monotonic featuring thing, that maybe some of your features are monotonic increasing and you know that up front and other features aren't. And in the standard ridge regression, there's no way to configure that. You're going to have to dive into CVXPy and build your own model. But still, the idea, that I think is still pretty cool. And again, I would love to see more blog posts like this because they really get the mind going. So, okay, cool little math trick. I'm into this. I've had a lot of fun implementing this in a notebook. This is the demo. This is pretty cool. But it's one thing to have a demo, which I've got, and hopefully this is. I see no questions, so I'm assuming there are no questions. But it's one thing to have a demo, right? That's all pretty well and good. But I was kind of wondering, you know, this. I was able to confirm some behavior that I liked locally. Can I maybe just write a scikit-learn implementation for this? I don't know if anyone will actually need to use it, but you know, I am still kind of in the mood of this could be super duper useful to some folks. So the way that I'm gonna go about that, usually what I do, is when I think I've got an idea that's kind of cute, if only because the not so much, even if it isn't the most useful thing out there, like obviously we're not gonna be adding this to scikit-learn. Like this is an interesting feature engineering trick maybe for some edge case, but scikit-learn cannot just willy-nilly accept all of this stuff. So what I typically do for these sorts of moments is I go to this library that I maintain called scikit-lego. And the whole point of scikit-lego is just be more experimental. So there's a whole bunch of experimental components in here. And yeah, this sounds precisely like one of those weird experimental components that someone might want to play with. So yesterday I just made an implementation of it. The cool thing here is that the implementation actually needs to use a cool NumPy trick that I feel like showing off because the NumPy trick is super duper useful and I think more people would like it. But this is still waiting for a proper review. I've notified my collaborator maintainer, but I can also imagine, you know, if Mate Katlishko would also like to have a look, he's also pinged here. This is not merged yet. This is up for review, but I do want to talk a little bit about the implementation, if there's no questions at least. Yeah, and I see that Mr. Kalishko is also responding. He's very much into Marimo dashboards. I totally agree, especially for teaching. I just want to have an exclamation point on that one. For teaching, it is just the best. But Mate also shares an interesting observation, which is that isotonic regression tends to overfit on 2 data points on the extremes. I would have to run a bigger benchmark for that, but it sounds plausible. I mean, what I can imagine, right? If I let's turn these off. Let's not do these this big benchmark over and over again. Oh, comment. Yep, and comment. Yep, very good. Let's also show isotonic regression and strictly positive. Let's do both here. And let's see if we can really draw that phenomenon out. So I'm going to reset here. I'm just gonna draw me like a little sort of data set over here. Yeah, and I think I know what you mean. Like what I could do is I could make like a little line over there and a little line over there. Like those are kind of outliers, you could say, right? Um, and then the question kind of is like, what would uh, isotonic regression do, and what would? Yeah, okay, so there you go. So in the case of an isotonic regression, which is I think the purple line. Yeah, so the purple line really makes a hard jump over here. Um, because of that one line, and you can kind of see that the other model is still kind of trying to smooth things out over here. So um, I would argue that both systems are not necessarily great at detecting outliers, but I can sympathize with the argument like, hey, see how the isotonic regression just makes a huge jump there? The fact that we're doing something more smooth here could also be seen as a benefit. Yeah, okay, that's a fair call. I would agree. Think about it when the model needs it and all that, but yeah, okay, isotonic regression in that sense. I've never really used isotonic regression, to be honest. I think it makes a lot of sense that it's in scikit-learn because it does feel like one of those classic sort of core models out there. I also think that the idea of a monotonic regression is definitely sound, and there are these edge cases for it where you really want it. In practice, I have found that just the histogram boosted gradient histogram models, those also do the monotonic trick. Usually I resort to those. I think you're also able to configure stuff like, okay, these columns have to be monotonic increasing, these have to be decreasing. Like there's extra settings you can set in those as well. So isotonic regression, in my mind, has mainly been useful for teaching. But I can imagine if I were in a situation where where isotonic regression would be super interesting, I would definitely start benchmarking it against this trick because it feels like this trick might have something to offer there as well. So yeah, great comment. Mate, if you have extra comments, by the way, do keep them coming because these are good. However, what I would like to do, I suppose now is, first of all, I want to show you the implementation. I think that might be good. And I think I've got too many windows open. Yeah, this is the VS Code session I was working in yesterday. So let's just start up my Jupyter notebook. There we go. Yep, there we go. This is basically I'm really just using the same data that is in the blog post just to explain how this monotonic featurizer would work. But let's pretend that we have a data set that looks like this, right? And I will also make this full screen, and I will also just zoom in a smidge. That'll feels a bit better. So I'm in Jupyter now, and I'm gonna just show you the implementation that I made. So I've got my my data over here. And again, you would kind of want to have a smooth line that can go through it, but maybe you also want to have one that's just a little bit more monotonic, right? So for that situation, I've worked on this monotonic spline transformer. It really tries to mimic the spline transformer inside of scikit-learn. In fact, this transformer is using the spline transformer from scikit-learn. The only thing that it does on top is it does the cumulative sum thing. Like that's the main thing that I'm doing here. And you can also see that, hey, I'm setting a number of knots. I am taking my I'm taking a sorted data set first, and when I plot that, I get the shape that I was interested in as well. This is the stuff I had before, basically. So nothing really new under the sun here, but I do just want to show, like, hey, fits transform, you are able to get these features out. And also combining it with a ridge, I'm building a pipeline over here, monotonic spline transformer, followed up by a strictly positive ridge regression, comparing that to the isotonic regression. Again, this was basically code I found on the original blog post. And I can also show here that, yeah, the scikit-learn pipeline, it does kind of work. The green line here is the isotonic regression, and the monotonic spline over here, you can just sort of see. You can kind of zoom in on this one, but you can definitely kind of see that it's just a little bit more smooth. That's also a feature you can see here. But the main point is that this is now in a PR, and this is something that I will hopefully get merged soon. But the thing that's interesting here isn't so much this monotonic spline transformer. Like the concept, I think, is pretty clear at this point. What I kind of want to zoom in on, and then that'll be the conclusion of today, But what I kind of feel like, oh, I need to import this maybe. Yep, there we go. If it's going to take too long to load, which it sometimes does, that sometimes is an indication of a broken client, but let me try to run this now. There we go. And I think if I put 2 question marks, I also get the entire implementation, which is what I'm interested in. Okay. So how is this guy implemented? Well, the thing is, in the previous demos, what I've always been able to do is basically reuse the train sets in my test set just to make the chart pretty. But if you're going to be doing this in scikit-learn proper, you have to assume the test set is, of course, different than the train set. So you're going to have to remember something in order to actually make the prediction. When I initialize this transformer, there's the knots, the degree, and that stuff. And when it's time to actually start learning something, all those things are in the on self. So these are things that I just reuse. But what do I do here? Well, remember that originally I was always talking about this little array X, and from that comes sort of a big array out, right? Like these are basically all sorts of functions that I'm applying onto that one array. Let's call this K for now. So that depends on the number of knots, etc. And well, first of all, I have a spline transformer, and then after that, I'm doing a commutative sum thing. Oh, but I don't just have one of these columns. I might actually have many. So I'm going to have to repeat this for column 1, and I'm going to basically have to redo the whole thing again for some other column too. F1 all the way up until FK. Pardon the notation here, but the main point here is that I'm going to have to repeat this. Oh, the camera is blocking some stuff. Let me just open up OBS such that I'm aware of what I'm drawing, but I think we're good. This is probably good enough. But anyway, like the main point here is that it's great that I have a way to turn one array into like a solid bunch of features. But what I am going to have to do is do it for all the different features in the original array. So the X that is going in here, like I have a fit function, right? So X goes in. The X that goes in here can definitely have more than one column. So, okay, how do I deal with that? Well, I have this self spline transformer thing over here. And basically what I'm doing is I'm just taking the original scikit-learn spline transformer, and for every single column in this dataset X that is going in, I'm just training a new spline transformer. It's kind of a nice way to keep things nice and separate. So that also means that I'm definitely going to be generating lots and lots of independent features. If you want to combine them in interesting ways, you're going to have to do that in the step after. But it is an important observation that everything I've done so far only works on one column, and here I have to accommodate the fact that I might have many. So that's definitely something I'm doing. So okay, I have my trained spline transformers. All that good stuff is good. But then what? Well, okay, let's think about that array that goes in here. So this is the first column of the original input X. What I'm gonna keep track of here is the sorted column variant of that. So I'm gonna take that entire column and I'm going to sort it. And then I kind of hear you think, well, why does that matter? Well, it matters because I am going to eventually also do a cumulative sum. And a cumulative sum will only make sense if the splines are ordered in the correct way, right? So every column needs to be sorted before I can do the cum sum thing. Okay, so that's what this sorted X is all about here. I'm just going to make sure that I've got some sort of a nice little order. And then what I'm also going to be doing is, given that I have my sorted X by so to say, then I'm able to do the cum sum thing on all of those sorted spline transformed datasets. So that's a lot to sort of keep in your mind, but hopefully it's clear that we need to do some sort of sorting in order to do transforming later, because all of those different spline transformers, if we lose track of the order, the cum sum just breaks. So it's a little bit of prep that we got to do. But then, in the transform, here's where I actually get to use, I think, my new favorite function inside of NumPy. Like I was actually kind of thinking, like, what's going to be like a good performant way to make sure that I can generate the right features going out, because I need to keep track of the order, etc. Right? Because the tricky thing is, if this is an x-axis, so to say, just from a one-axis perspective, I could have, let's say, I don't know, the value 10 and the value 11, and I've got the value 11.5. Like, maybe those are values that I've actually seen before. Then for those values, I have some output from the spline transformer, let's say, right? That's, those are the features that the scikit-learn spline transformer are able to create. But what could happen, of course, when I do like inference at test time, then I could have whatever weird value that's in between there. So I need some sort of way to properly interpolate between all of those sorted features. And for that, it turns out that there's actually a NumPy interpolate function that will just really solve this entire problem for you, and it is just the best. The easiest way to explain how it works in detail is to just go to the NumPy docs, but I am over the moon excited about this one, because it feels like one of these things that interpolation happens so many times, and just having a very solid function for that is just super nice. So numpy.interp, and yeah, there's a little preview of how it works. I'm just going to zoom in on. So the way the interp function works is it has 3 inputs. So it has the x values that you want to interpolate, and then you've got x values and then y values that are known up front. So if you have a little look at the image below, the array x over here belongs to all the x coordinates for all these blue points. Then you've got the y over here that belongs to all the y coordinates for all these blue points. And then those are the two, like the second and third argument. The first argument of numpy interp is just all the x values that you want to get a y value for. And then this is just really going to make sure that everything is nice and interpolated on your behalf. And that's the combination that you need. So first of all, you need to make sure that for all of these different columns, you are keeping track of a separate spline transformer. Then you have to make sure that that column is nice and sorted, such that the thing that you're going to generate, the cumulative sums, that those can be calculated nicely. And then at test time, then you're going to apply this interpolates trick on all of those separate columns. And when you do that the right way, that's when you get something that looks, then you get features out that kind of look a bit like this. This is something you can totally do like at prediction time. And it's also, I have to run all these cells of code technically, but let's just actually do that. Kernel, restart, run all cells. I did this yesterday. But this is everything I think that you need in order to get a good implementation of this going. And let's remove this implementation detail. We can definitely see that this kind of nicely works. One thing to pay keen attention to over here is that there's a train data set, and I've got a test data set over here, and the test data set is of course different. I can also just increase the granularity. Okay, I can't do that. Oh, then there might be a bug actually. Hang on, this works. Let's just rerun the whole thing one more time. Restart kernel, run all cells. X test is, yeah. I think I should be able to do this. We're just going to run this once, and if it doesn't... Okay, so this is now causing an error. And I think I spot the error. If I move it back, yes, okay, hang on. If I put this back and set it to 100, then it also errors out, and it's probably because there's a code block below over here that redefines X. If I were now to, this is the classic Jupyter stuff. That you sort of, I ran a cell below, and that breaks the cell above, and I forgot about that. And kind of why I like using Marimo sometimes, because Marimo sort of fixes that. Still stuff to like about Jupyter. Just to be clear about that. But somehow I forgot about that. So scikit learn pipeline import make pipeline. Right, there we go. And now if I update this, it does work. So that's the point I wanted to make. The granularity of the test set can be independent of the granularity on the train set. And in the basic demo, that wasn't the case. If you really want that to work properly, you're going to have to think about the interpolation stuff. But I did that. This entire implementation is up for review. If you're curious about it, what I'm just going to go ahead and do now, escape full screen. I need to move my cursor here and then escape full screen. If this sounds interesting to you and you're interested in just looking at some of the details, this is up for review. So if people want to, you can review my code. I will gladly accept any commentary. Yeah, I also added a whole a few tests, and I also added like a good section for the docs, a bunch of images and stuff like that. So I think we're almost we're getting close to time. So this week it wasn't like a grand thing that I really wanted to show here, but I do think it's kind of nice and inspirational that if you're mindful about the features that you generate, you suddenly can get monotonic behavior from your model out as well. And that's just it's a bit of a party trick, but it's a nice one. And I really, really dig it when people blog about that. So anyone who's listening, if you've ever gotten a brain fart like this that you would like to showcase, for God's sakes, please start a blog. We need more of this in data science land. A lot of people that I know sort of stopped blogging when they started having kids, which is fine. Life is busy. But blogging, I love it when people do it. Even if you only blog twice a year, like a blog post like this is just a good read. So just want to give a shout out where shout outs due, because this is stuff that really keeps the field fun for me. But yeah, this is everything I wanted to share. Like it's a neat little deep dive into a blog post that I read that I think has an idea that's at least pretty interesting, I would say. So yeah, hopefully this was exciting. I'm gonna take all the code stuff that I've got here, and I will figure out a way to share that. We have a YouTube YouTube appendix repository on GitHub. I'm gonna add that there, and I'll add that to the show notes when this is done. But yeah, I think this is also like a good time to maybe quit this one, because it's kind of fine to have a short live stream once in a while. The only thing that I do want to maybe mention is actually two mini announcements here. So a couple of announcements. One, I don't promise when, but yeah, the next version of Scikit Lego will have this transformer in there if you're interested in playing around with it. So feel free to look forward to that. The second thing is that if you've been paying attention to our socials, we have just announced a Scikit-learn official certification program. Feel free to join our Discord if you have extra questions about that. We will gladly answer any question that you might have. The whole point of the certification program is that you can now get a high-quality certification that has been designed by Scikit-learn core maintainers, and when you or your company pay to get certified, that money goes to fund Scikit-learn. I'm super eager to see that. I've seen a bunch of great Scikit-learn courses in the past, but I've also seen a couple of bad ones. And something about the fact that we now have an official one, great. Like, I'm really looking forward to that. So if that sounds interesting, feel free to join the Discord and ask us anything about that. It also feels like I can't really mega announce anything just yet, but it feels like we're going to announce like some other stuff in the same Discord channel maybe next week. Something new, open sourcey product, something maybe. No promises, but definitely something to also look forward to. Someone is asking, do you think you'll have a voucher for the certification? What do you mean with voucher? Like you get like a diploma or plaque, or like you get a certificate. Like when you take the certification program and you pass, you have to pass a test, by the way. Then you do get a proof of being certified. At the moment, there are 3 levels. I think the first level is the thing that's live right now, but there's also more than one level of certification that you can take. One thing I also want to say about the certification that kind of drew me in. At some point, people asked me like, "Hey, Vincent, can you take the certification test and let us know what you think?" And I figured, okay, let's just see if I can sort of pass this test with no studying whatsoever, and just kind of YOLOing, going through the ABCD questions and like totally forgoing on the programming exercise. Can I still manage to pass with my scikit-learn knowledge? And the answer is no. I failed. Um, um, oh, people are asking if there's like a discount code. So I don't have a discount code. There are prices that we have in our mind and have communicated in the Discord channel. If the price is too much for you, definitely like reach out and let us know about it. We just started this, so if it turns out that the price that's listed right now is prohibitive, then we do want to know about it. Like, the thing with the certification program is that we are, of course, eager to make sure everyone who wants to get certified is able to get certified. However, we also want to make sure that you're not able to cheat, and that one thing also makes it a bit more expensive for us, because if you want to get certified, it also means that proctoring is involved. Like, we need to figure out some sort of way to know that you're not cheating, so to say. So there's also a price tag, unfortunately. I think we're also going to change the tests every half year or so. I don't know for sure if that's like a half year or a different number, but we cannot make it free, unfortunately. Partially because we like the idea that this is eventually also going to fund scikit-learn, but also just because of the reality of proctoring. If we really want to make sure people don't cheat, which, if you want the certificate to be valuable, we have to guarantee that people have a hard time cheating, then there are costs involved. But if it's prohibitive, do let us know, because we definitely want to know more about your situation, and we're definitely eager to think along at least. But yeah, so Discord is the place to ask us questions about that. If you're interested, I think my colleague Arturo has started sharing some practice questions, like some of the questions that have made it through to the exam committee, so to say. And also, if people have questions on like how to best prepare, we can answer questions about that as well. One thing I can say, actually, and I should mention this because a lot of people don't know about it, but did you know that there's actually a scikit-learn MOOC that's official? And of course, if you're typing MOOC scikit-learn, don't go to the Datacamp or Coursera one. It's not the one that I'm interested in, but scikit-learn official MOOC. There we go. So like, don't click any of the don't click any of the sponsored links. The thing you want to go to, and this is free, by the way. There is an official scikit-learn MOOC. It's on an INRIA website. This would be a pretty solid place to start. If you want to pass the first certificate, I don't think you have to go through the entire thing, but this is the official scikit-learn MOOC. Like, the scikit-learn core team has been working on this, and it's it's got a lot of the good content. So this would be a good place to start. But yeah, I don't know if we have a practice exam, but I'm also not in charge of the certification program, so I want to make sure that you get the right answer. If you have specific questions, come to our Discord, ask questions there, because colleagues of mine will gladly answer for all the details that you're interested in. One of the colleagues, by the way, that has been working on this. And one really cool thing about Arturo is that I interviewed him, and this week. It is about the scikit-learn docs. So Arturo, I did link the MOOC in the podcast. So if you go to the show notes inside of these show notes, right? If you go to the bottom of them here, it has the link to the MOOC. So the link should be there. If you've been watching, someone is complaining about not having the link. If you didn't see that link on another player, then like a podcast player, that's definitely possible. But the YouTube one, for sure. But yeah, like, this is a really fun conversation I have with him. So the cool thing is that Arturo is in charge of a bunch of things, one of which is the scikit-learn docs, and he's been doing a bang-up job, like, maintaining that. Oh, you're asking about the Spotify one. Let me check. Sample space Spotify. Okay, that goes on top, so that's good. And if I go to that episode, and if I accept all the cookies, if I hit show more, then also there, to me at least, it seems like there's a link. If it's not rendering on your end, definitely let me know. But yeah, it's a fun episode. The main thing that people sometimes aren't aware of is that the scikit-learn docs actually come with a recommender, but the recommender is built with scikit-learn pipelines using super basic like TF-IDF featurizers. But the thing that I love about the recommender is people assume it's done by hand, like it's manually curated, but it's not. Like if you go to the bottom of a section, if you want to see related things, all of that is done with scikit-learn. It's kind of like a silent recommender of sorts. But if you want to learn about the details, this podcast will answer all the questions. Because they wanted to do it in like a privacy preserving way, so it's an item to item recommender, and it's really done up front and etc. But the fact that it's just no complaints have ever been made from it is still kind of cool. It's an unconventional way to build a recommender, and it's sort of an unconventional place to put a recommender, but the scikit-learn docs totally has a recommender. So yeah, just wanted to mention that as well. Yeah, I think we are at time now. Hopefully, I answered all the questions, and I hope that people like genuinely found this to be just kind of interesting. Monotonic features, when you need them, they are great. Sometimes there's good business reasons to keep some things monotonic, and yeah, we have a new featurization trick. That's the main thing. This new spline transformer might go live soonish. Do let me know, and yeah, hopefully people enjoyed this one. I'm gonna stop recording now. If there's any questions, do let me know, and I'll be on the Discord. So if you have any suggestions for like stuff I gotta do next week,